In 1977, two spacecraft were launched from Earth with a very specific goal: to explore the outer planets of our solar system. The mission was designed to last a few years, at most, a decade. No one involved in the project expected that nearly half a century later, those same spacecraft would still be transmitting data from beyond the edge of solar influence. They were called Voyager 1 and Voyager 2. Their launch coincided with a rare planetary alignment that occurs roughly once every 176 years. This configuration made it possible to use gravity assists, carefully planned flybys of giant planets that allowed the spacecraft to gain speed and change direction without expending additional fuel. It was an elegant application of orbital mechanics, turning the solar system itself into part of the propulsion system. The original plan was ambitious but limited: Jupiter and Saturn for both spacecraft, with Voyager 2 continuing onward to Uranus and Neptune. Interstellar space was not part of the mission design. Each Voyager carried a suite of scientific instruments: cameras, magnetometers, plasma detectors, cosmic ray sensors, and radio science equipment. Power was supplied by radioisotope generators, converting heat from decaying plutonium into electricity. There were no modern onboard computers, no autonomous navigation systems, and no artificial intelligence guiding decisions. Every maneuver, every adjustment, every instrument activation depended on commands sent from Earth, traveling at the speed of light. The early years of the mission transformed planetary science. At Jupiter, Voyager revealed turbulent atmospheric dynamics and intense radiation belts, but perhaps most unexpectedly, it discovered active volcanoes on Io, the first confirmed volcanism observed beyond Earth. Jupiter was no longer just a gas giant. It was a dynamic system shaping its moons through gravity and radiation. At Saturn, Voyager mapped the structure of the rings in fine detail and examined Titan's dense atmosphere, hinting at complex organic chemistry taking place far from the Sun. These observations fundamentally changed how scientists understood both planets and moons, revealing them as evolving environments rather than static worlds. After Saturn, the paths of the two spacecraft diverged. Voyager 1 was redirected upward, out of the plane of the solar system, placed on a trajectory that would eventually carry it toward interstellar space. Voyager 2 continued outward, becoming the only spacecraft ever to visit Uranus and Neptune, discovering new moons, strange magnetic fields, and powerful winds that demonstrated even the most distant planets remain active. By the late 1980s, the planetary phase of the mission had ended. Under normal circumstances, this would have marked the conclusion of operations. Instead, Voyager entered a new chapter. As the spacecraft moved farther from the Sun, they began exploring the outermost regions of the heliosphere, the vast bubble carved into interstellar space by the solar wind. Inside this bubble, charged particles streaming outward from the Sun dominate the local environment. Beyond it lies the interstellar medium, shaped by distant stars and ancient supernovae. Crossing this boundary was never part of Voyager's original objectives, yet the spacecraft were uniquely positioned to attempt it. Over time, their instruments recorded gradual changes, decreasing solar particle density, increasing cosmic radiation, and shifting magnetic conditions. Eventually, Voyager passed through the termination shock, where the solar wind slows dramatically and entered the heliosheath, a turbulent region marking the transition between solar and galactic space. Then, in 2012, Voyager 1 crossed the heliopause. This moment represented something unprecedented. For the first time, a human-made object entered interstellar space. The measurements were unambiguous. Solar particles dropped sharply, galactic cosmic rays increased, plasma density rose to levels consistent with interstellar material. Magnetic field orientations changed. This was not symbolic. It was a physical transition into a different environment. Voyager 2 followed in 2018, crossing the heliopause at another location, confirming that this boundary is not smooth or uniform, but shaped by interactions between solar and galactic forces. Together, the two spacecraft provided the first direct measurements of interstellar space. They revealed that our solar system is moving through a diffuse plasma threaded with magnetic fields and energetic particles, a medium that plays a role in star formation and influences how planetary systems evolve. Even now, decades after launch, Voyager continues to transmit data, but maintaining operations requires careful management of dwindling power. Each year, available electrical output decreases, forcing engineers to shut down instruments one by one. Every remaining watt is allocated deliberately, prioritizing sensors that still provide unique measurements of this distant environment. Today, Voyager 1 is more than 24 billion kilometers from Earth. Its signal takes over 22 hours to arrive. Any command sent in response requires another 22 hours to reach the spacecraft. Communication happens on timescales measured in days, not seconds. Eventually, likely in the early 2030s, Voyager will fall silent. Its remaining instruments will shut down, and its transmitter will cease operation. From that point on, both spacecraft will become inert objects, continuing their trajectories through the Milky Way for millions of years. Attached to each Voyager is a gold-plated record containing images, sounds, music, and greetings from Earth. It was never intended as a realistic attempt at communication, but rather as a cultural snapshot, a small archive of humanity at a particular moment in time. Yet, the lasting legacy of Voyager is not symbolic, it is scientific. The mission showed that exploration does not always proceed according to plan. A spacecraft built to study 4 planets became humanity's first interstellar probe. It provided evidence of geological activity on distant moons, mapped magnetic environments around ice giants, and directly sampled the space between stars. Voyager demonstrated that reaching interstellar space does not require advanced propulsion or futuristic technology. It requires careful engineering, long-term commitment, and instruments sensitive enough to detect subtle changes in an environment that is quiet, sparse, and vast. Voyager no longer sends images. It transmits measurements, particle counts, magnetic field strengths, plasma densities. These streams of data may seem abstract, but they represent humanity's first direct contact with the material between stars. The spacecraft is not heading toward any particular destination. It is simply moving forward, following the inertia imparted at launch nearly 50 years ago. Long before it approaches another stellar system, it will be silent. What remains is its path, a thin line extending outward from Earth into the galaxy. Voyager is not a story about speed or spectacle. It is a story about continuity, about building something carefully, launching it once, and allowing physics to carry it far beyond its original purpose. In a universe measured in light years, Voyager advances kilometer by kilometer, slowly, steadily, without drama. And with every signal it sends, it reminds us that even modest machines, guided by patient science, can leave the solar system and begin humanity's first quiet journey into interstellar space. Beyond its position in space, Voyager is also teaching us how interstellar environments interact with planetary systems. The spacecraft has measured fluctuations in magnetic field strength, changes in plasma density, and variations in cosmic ray intensity that could never be inferred from inside the heliosphere. These observations show that interstellar space is not uniform. It contains structures, pressure gradients, and magnetic boundaries shaped by nearby stellar activity and ancient supernova explosions. This matters because every planetary system exists inside a similar galactic environment. The conditions Voyager is sampling today influence how stars form, how cosmic radiation penetrates planetary atmospheres, and how long-term exposure affects habitability. Our solar system is not isolated. It is embedded in a dynamic medium that slowly evolves over millions of years. Voyager has also helped refine models of how stellar winds carve protective bubbles around stars. These heliospheres act as shields, reducing the amount of high-energy radiation reaching inner planets. By measuring where our own heliosphere ends, scientists can better understand how effective this protection is and how it might differ around other stars. In a sense, Voyager provides a reference point. It tells us what lies beyond the sun's influence, allowing astronomers to compare solar conditions with the broader galactic environment. This context is essential when studying exoplanets, especially those orbiting active stars, whose stellar winds may be far stronger than our own. The data Voyager continues to send back is incremental, quiet, and highly technical. But taken together, it forms the first direct profile of interstellar space surrounding our planetary system. No telescope on Earth could provide this information. It requires instruments physically present in that environment. This is what makes Voyager unique. Not its distance, not its longevity, but the fact that it is still measuring a region of space humanity has never explored before. Every packet of data adds another small piece, to a picture that will take decades to fully interpret. Long after Voyager goes silent, scientists will continue analyzing its measurements, refining models of heliospheres, cosmic radiation, and galactic plasma. Its journey may appear slow on human timescales, but in scientific terms, Voyager has already crossed one of the most important boundaries in astronomy, the edge of our star's domain.